got a few people gone today, but many told me they were going to be gone. So, how we doing? All right. Every week to go over. How was everybody's Halloween? Good. Good. Any questions at all over anything before we get into some new stuff today? Sorry. Sure, you're fine. No worries. Things are good. So we have a test next Friday. We did identities. I think the last test ended with law of cosines, right? We did law of sines and cosines in the last test. So we started this stuff for this exam with identities, and then we did sum and difference identities. That was the last section we just did for the last week. And then today we're going to start talking about double angle, half angle, and product sum formulas. That sounds like a lot of words. This is the last section that will be on the test. So your exam will be over 7-1, 7-2, 7-3. Your exam is next Friday. Okay. So just to give you a heads up that it's just those three sections that'll be on the exam. Okay. All right. So good news is that these formulas really aren't, I mean, you'll probably memorize them anyway just because you don't want to have to redo them every single time. But these formulas that we're going to talk about today really aren't new. Yes. Oh, yeah, you can have one. Sorry. My bad. Didn't even think about it. There you go. Whoa. All right, so these formulas really aren't new. So all these formulas that we're going to talk about today come from the sum and difference formulas that we've already talked about. So what we're going to do is we're just going to manipulate those sum and difference formulas. And with the half angle formula, we really manipulate the double angle formula, but that double angle formulas come from the sum and difference formulas. So everything here is going to come from sum and difference formulas. Okay. Like I said, though, when we get to the final form, we'll probably just go ahead and try to memorize it rather than reproduce it every single time. But it's not really anything that's new. It's just a manipulation, if you will. Okay. All right. So looking at this first one with sine of 2x, how can I rewrite 2x as a sum? X plus x. That's great. Yep, exactly right. Okay. And now again, remember our sum and difference formulas. Well, our sum formula for sine, if I do it with alpha plus beta, my phone is blowing up and is distracting me. I can just see email. Sorry. So this is sine of alpha, cosine of beta, plus sine of beta, cosine of alpha. Using our sum formula here, what can I treat for alpha and what can I treat for beta and how we just rewrote this? What can I use for alpha? X. And what can I use for beta? X. Yeah. So what are we going to get if we use alpha or X for alpha and X for beta? What are we going to get?
Sine X, cosine X. Sine X, cosine X.
Good. That's exactly right. So we use the X for the alpha and the X for the beta. We get sine X cosine X plus sine X cosine X. How many sine X cosine X's do you have then? 2 of them, yep. So just to write this here so I can box it in. There's your double angle formula for sine. We call it a double angle formula because it's double the x, right? It's 2 times the x. That's why we call it a double angle formula. That was it. Like I said, it literally comes from the sum formula for sine. Do the same thing for tangent. What was your sum formula for tangent? If I do tangent of alpha plus beta, what was that one again?
Tangent alpha plus tangent beta.
Good. Yeah, it's the sum of the tangents on top, product of the tangents on bottom, and then the room with the sine in the middle flips. So just like we did in the previous one, rewrite your 2x as x plus x. So now apply your sum formula for tangent, and what do you get?
Tangent x plus tangent x over 1 minus tangent x times tangent x.
Good. Yeah, so we get tangent x plus tangent x on top, 1 minus tangent x times tangent x on bottom. And to clean that up a little bit, how can you rewrite the top? 2 tangent x. And how can you rewrite the bottom? 1 minus tangent squared x. Good. Exactly right. Everybody okay with those two? Notice that my next one for cosine 2x, I've got equal signs in there a couple of different places, all right? Okay, so it's not a typo or anything along those lines. I really do mean that we're going to do this kind of 3 different ways. Okay, the first one we're going to do exactly the same way we've approached the other two. We're going to think of this as cosine of x plus x, just like we did the other two. What's your sum formula for cosine?
Cosine alpha, cosine beta. Sine alpha, sine beta.
And it's minus in the middle, right? Yeah. Oops. I don't know why I wrote cosine. Remember, your sum formula for cosine does cosine, cosine, sine, sine, but the SIGN in the middle is flipped. All right, so using our sum formula then, how can I rewrite the cosine of x plus x?
Cosine x minus sine x, sine x.
Good. And then if we clean that up a little bit, we get cosine squared x minus sine squared x. So that's one form of cosine 2x. Notice it looks a little bit like our Pythagorean identity, doesn't it? It's a minus in the middle rather than a plus. Right? However, there will be occasions, and including here in a little bit, there will be occasions in which I'd like to get rid of one of these trig functions and write it in terms of the other one. So I can use the Pythagorean identities to help me rewrite this. What can we plug in for, say, cosine squared x? What can I replace cosine squared x with?
1 plus sine squared x minus.
Here we go, minus sine squared, good. So we can also write it as 1 minus sine squared x for the cosine, and I have a minus sine squared there as well. So another form for cosine 2x is 1 minus 2 sine squared x. There will be, well, in a little bit when we do half angle formulas. We'll want this one. But there will be occasions when we start doing some solving of trig equations that one of our big techniques will be to write everything in terms of the same trig function. It's harder to solve trig equations if you've got mixed matched trig functions, like all in terms of the same one. So if you have something like a cosine of 2x and a sine of x, you'd want to use this identity first. We'll talk more about that when we get to it. Okay, but that's one of the reasons why we want to play around with this identity. Notice we started to get this one from going back up here and replacing the cosine squared with 1 minus sine squared. Instead, we could have replaced the sine squared with what? Instead of replacing the cosine squared, we could replace the sine squared with what? 1 minus sine squared. 1 minus cosine squared there. All right. And then if we simplify this one, we get the third form of your cosine of 2x. That was why I have the 3 equal signs there, because there's 3 different forms. All right. So sine and tangent just have the one form, but cosine of 2x has 3, and depending on the context, we'll use each of them. Okay? So let's see if we can play around with these a little bit. Hey, this looks like a familiar problem. You're given information about a trig function, and it asks you to compute different trig functions of, in this case, different angles for that, right? We just did ones like this with the sum of difference, didn't we? So the first thing we probably want to do, ignoring what it's asking us to do to compute, what do you think we want to do first with this information? Yeah, let's make a triangle, right? Make a reference triangle for us so that we can read the trig values off. What quadrant am I going to draw my reference triangle in? With the given information, what quadrant are we going to draw the triangle in?
Third.
The third? Good. Because it says the angle is in between pi and 3 pi over 2. So we're talking about quadrant 3. We're given information about cosecant. So what sides can we label?
Hypotenuse and opposite.
Hypotenuse is going to be
17.
good. And the opposite will be negative 15. Good. Because cosecant is 1 over sine. So it's hypotenuse over opposite. So your hypotenuse will be the 17. Remember, the hypotenuse is always positive. So our opposite side, like you will use negative 15. Can we figure out the third side? Be a lousy problem if we can't figure out the third side, right? What will we get for the third side? 8. What kind of 8?
Negative.
Negative, good. It'll be a negative 8. If you use your Pythagorean theorem, you would do square root of 17 squared minus 15 squared. So you'd have 289 minus 225 gives you 64. Square root of 64 is 8. We're using negative, though, because we're to the left of the y-axis. All right, for our reference triangle. Okay. All right, so now we want sine of 2 alpha. Well, remember, the only thing we have here, we have a reference triangle for alpha, right? That's what we have. We don't have 2 alpha. We have a reference triangle for alpha. So if I want to try to use this reference triangle to give us the values that we need to be able to we need to use those formulas, one of those formulas that we just came up with on the previous page. So for sine of 2 alpha, how can we rewrite that? Using our identity, how can you rewrite sine of 2 alpha?
2 sine x cosine.
Yeah, so the 2 sine alpha, cosine alpha in this case, because I'm using alphas, but you're right, that's the right formula. Yep. Can we calculate sine of alpha now? Sine of alpha is good, negative 15 over 17, and cosine of alpha is good, negative 8 over 17. And I don't care if you simplify the arithmetic at all. That's what a calculator is for, right? Just leave it like that. Is that okay? The other two you're going to do similarly. We've already got the triangle set up, so there's not any additional triangle work to do. For your cosine of 2 alpha, again, use one of the formulas that we have for cosine of 2 alpha, one of the double angle formulas for cosine. Tell me one of them. What's one of your cosine double angle formulas for cosine?
Cosine squared x minus sine squared x.
Good. That's one of them, right? And you just told me a minute ago that cosine is negative 8 over 17 and sine was negative 15 over 17. So we'll get negative 8 over 17 squared minus negative 15 over 17 squared. What do we get? Oh, this one I actually am going to simplify because I want to compare it with the other one, at least one of the other ones, to make sure that we really are getting the same answer, since they're identities. That's 64. That's 225. 225 minus 64 is what? 161? If I did my arithmetic right. So I should get negative 161 there over 289. Check my arithmetic, but 225 minus 64. This should be negative. What was another one of the formulas for cosine of 2 alpha? What was another one that we had?
Minus sine squared alpha.
It was 1 minus 2 sine squared alpha, right? So you'd have 1 minus 2 times negative 15 over 17 squared. Well, 15 squared is 225. Multiply that by 2, you get 450 over 289. You need to count the denominator. 450 minus 289. Oh, look at that. It's 161 again. So I really do get the same answer. Well, you should get the same answer, right? We're saying these are identities. It doesn't matter what you plug in. You should get the same number, right? Right? So you should get the same thing. Now, on your exam, I would not expect you to do it twice, right? If I'm asking you a problem like this, do it one time. Okay? But I just wanted to illustrate that you really do get the same answer using either of them. And if you use the 2 cosine squared alpha minus 1, you'll get the same answer. Okay? It does not matter which one you use. For tangent of 2 alpha, what do we replace that with? Yep.
1 minus tangent squared.
Good. Yep. The top is 2 tangent alpha. The bottom is 1 minus tangent squared alpha. And in this problem, tangent of alpha is equal to what? 15 over 8. Good. Yep. Again, don't care if you simplify it. I didn't care in the previous problem if you simplified it. Again, the only reason why I was simplifying is so that I could, show you that we were really getting the same answer in either case. Again, not really a new problem, right? Just illustrating that we can use the same new formulas in the same types of problems we've done before. What questions do you have? Is this okay? Yeah. All right, let's see what's next. Look at that, identities. Wonderful. We love identities. All right, so this one's asking us to verify that sine of 2 theta is the same thing as tangent theta times 1 plus cosine of 2 theta. It might be a little ambiguous for the notation. The tangent theta is just being multiplied by that. This is not inside the tangent function. Just the theta is. Might look a little ambiguous, but if it were inside the tangent function, this problem would get a lot harder. Okay. We don't want that inside the tangent function. Which side do you want to work on? I'd probably work on the right side. There's more stuff going on, right? All right. Notice that in this particular problem, well, there's lots of stuff going on, but notice that we're trying to get this down to a single term, right? We're trying to get it down to a single sine of 2 theta. Remember for cosine of 2 theta, I've got 3 choices in which I can plug in there. You can, and it's perfectly fine to put any of the 3 to start in, okay? But if I want to get this down to a single term, a single sine of 2 theta, I probably really, really want this plus 1 to go away, right? It's probably the easiest thing to get rid of if I can is get that plus 1 to go away. Is there one of the 3 forms that you could use for cosine of 2 theta that if I substitute it, the plus 1 would go away? Which one can I use?
1 minus 2 sine.
So if I use the 1 minus 2 sine, I would still be adding my 1s. So use the other one, right? Use the one that has the minus sign in it. Good. Yeah, so if I use the 2 cosine squared theta minus 1, then I just have tangent theta times 2 cosine squared theta, right? Because the 1's cancel. I'm not saying that's the only way to approach this problem, by the way. You could have used one of the other ones, and you would get, if you go through everything correctly, you'll get there. It was just that if I use that one, then the 1's go away, which helps me out, right? I'm down to a single term, right? I don't have a sum anymore. Okay. What do you think we should do next?
Do we do anything with tangent, like make a sine of cosine?
Well, if you don't know anywhere else to go, that's what I would do. Let's make the tangent be sine over cosine. That is one ugly looking theta. How does that help us? Yeah, one of the cosines cancel, right? When that cancels, you get 2 sine theta cosine theta if I rearrange. What are we trying to get to? Sine of 2 theta. Is that equal to sine of 2 theta? Yeah, that was our formula we just came up with, right? So there we go. Questions on that one? Or is that okay? See if you can do the next one. Work on that one for a minute or two, and then we'll chat about it. Which side did you start on, left or right? The right. Sounds like a good plan. So, what did you try next?
I changed up to 1 plus 2 1 plus 2 plus 9 squared x and so on.
Okay. You did this one? Know what you said? Okay. And then the ones canceled? Okay. This is not the only way to go about it, by the way. I probably would have started with a different one. Just to, I'll explain why here in a second. This is okay. What did you do next then?
Well, I multiply by 1 minus sine x, top and bottom.
Okay. I like that because that's a conjugate trick we came up with before, right? Because what does that make your denominator equal to then?
1 minus sine squared x.
Good. So multiplying top and bottom here by that 1 minus sine of x gets that difference of squares in your denominator. And in particular, it gets you that 1 minus sine squared x in your denominator, which you can replace with cosine squared x. And then what happens? Yeah, the cosine squared x's go away, and you're left with exactly what you want if I actually write a minus sign instead of a plus sign. Yeah, that's great. Anybody else approach it differently? Did you plug in something else different than cosine of 2x in the top? Yeah, okay, you can do it that way too. What if you did, oh hey, I could write. What if instead you plugged in 1 minus 2 sine squared x for your cosine of 2x? Which, this is probably the way I would have attacked it. The reason why is because notice that what I'm trying to end up with only has sines. So if I could get rid of the cosine and make it in terms of sine to start with, that's what I would have done. That's how my brain would have worked. There is absolutely zero wrong with the other way. If that's the way you did it, perfect. It's great. Okay. I'm just telling you that the reason I would have thought of it to do it the other way was because now I have everything in terms of sine, which is what I have on the left-hand side. And the only reason why is because when we start talking about solving trig equations, a lot of times we're going to want to put everything in terms of the same trig function first. Okay. But there is literally nothing wrong with this. This is really good. Okay. All right. So notice that gives you 2 minus 2 sine squared x on top. Do you see anything you can factor out of the top? There are 2. Good. And now, yes, this is equal to cosine squared. But I can also factor this, right? This is a difference of squares. That factors is what? Yeah, the 1 plus and 1 minus sine x, right? And then same idea here. Your 1 plus sine x's cancel. And you get to the same place. There is more than one way to get to the final answer in these identities a lot of times. These are two separate, valid ways to verify that identity. As long as you're using allowed steps and using proper identities at each step, the proof of the identity is valid. There's nothing wrong with it at all. Okay, so do it how you see to do it. Questions on that one at all? Is okay? All right. Let's switch gears a little bit then and develop what we refer to as the half angle formulas. So notice that it looks like I made a typo because it looks like I wrote cosine of 2x twice. I really did mean to write cosine of 2x twice. So let's talk about how we get this particular formula. All right, so one of the ways that we can rewrite cosine of 2x is doing 2 cosine squared x minus 1. That's one way to get there. Now notice that the title of this particular subsection, if you will, is called the half angle formula. The reason why this is going to be called the half angle formula is notice that the argument in here is half of the argument here. That's where the half comes from. Okay? So what we're going to do to create the half angle formula is I'm going to solve for cosine x. Okay? So we will add 1 to both sides and divide by 2. Before I go on and do a little bit more with this particular equation, I do want to stop here. And this is an important form of the double angle identity. We just rearranged the double angle identity for cosine a little bit. Notice that the power on your cosine here is a 2. The power on the cosine here is a 1. Even though we doubled the argument, we've reduced the power on the cosine by 1. We actually refer to this as a power reducing formula. We've dropped the power from squared to the first power. This is important. This is important in calculus. In particular, it's important in Calc 2. Okay. So if you're not going on to Calc 2, then it's not really that important for you, but in calculus, it does pop up again. Okay. So that's why I stopped to mention it. All right, at this point, if I wanted to solve for cosine, I would need to take the square root of both sides. But remember that when you do the square root of both sides, you get plus or minus, right? Now, cosine is a function, correct? When I plug one thing in for cosine, I get one thing in or one thing out of the function, right? So this can't equal both the positive and the negative for the same value of x. So this is a little deceptive. Even though we write it as plus or minus, we don't really mean plus or minus. We really mean that this is a decision we have to make. This is, you use the appropriate sign depending on the quadrant that x is in. Okay? All right, so let me do this with an example. Let's skip ahead to the next page and look at example B. Okay? Skip ahead to the next page and look at example B. This one's asking us for the exact value of cosine of 7 pi over 12. Okay? According to our half angle, this is not one of the ones that we know, correct? This is not one of the exact values that we would know. But notice that 7 pi over 12 is half of 7 pi over 6. We also did this with a sum formula, right? But we're going to do this with a half angle formula. So this must be equal to plus or minus square root of 1 minus cosine of 7 pi over 6 over 2. Oh, sorry, not minus, it's plus. Sorry. But again, it cannot be equal to both of them, right? It can't be the positive and the negative. It can only equal one of them, right? We have to make a choice. Is it positive or is it negative? So I look back at the input. I look at the 7 pi over 12 and say, what quadrant is 7 pi over 12 in? Sorry, this is the second quadrant, right? Because pi over 2 would be 6 pi over 12. We're just a little past that. If we're in quadrant 2, is the cosine positive or is the cosine negative? Negative, right? So I don't want the positive, I want the negative value. Okay? And this is because 7 pi over 12 is in quadrant 2. Okay? Notice I didn't look where 7 pi over 6 is. I looked where 7 pi over 12 is, right? 7 pi over 6 is in a different quadrant. Okay? I don't want to look at that one. I want to look at where 7 pi over 12 is to tell me if I'm using positive or negative. So then finally, we would compute what cosine of 7 pi over 6 is equal to. It's a pi over 6 angle, so we would use root 3 over 2. 7 pi over 6 is in quadrant 3, so it is negative as well, but that's where we get the minus root 3 over 2. Again, don't care if you simplify this at all. But this would give you the exact, another form of the exact value of 7 pi over 12. Okay? Again, the trickiest part of using these half angle formulas is determining, do you want the positive or do you want the negative? That's kind of the trickiest part. The rest of it is just a matter of the formula. Again, the reason why we call it half angle formula is because the inside of this is half of the inside of that. Okay? In particular, if you want, if I go back up here to the half angle formula, you can also write this as cosine of x over 2 is plus or minus square root of 1 plus cosine x over 2. If you really want to emphasize that it's half of what the input is on the other side. Half of the input on the other side. Okay. I like the other ones without fractions inside my cosine, but it's the same idea. The important thing is this is half of that. Or that's double that, whichever way you want to think about it. We can do the exact same thing using your other one of the other forms of cosine of 2 theta. I can replace cosine of 2x with 1 minus 2 sine squared x. Rearrange. Divide. Take the square root. Notice that the form of the half angle formula for sine is almost the exact same thing as it was for cosine, isn't it? The only thing that's different is the minus sign in the middle. again, this is not always plus or minus. A plus or minus is really a choice, right? Okay? It's not both the positive and the negative. It's choose, is it positive or is it negative, depending on what quadrant the input is over here on the left-hand side. It's not like when you have plus or minus in the quadratic formula, right? Plus or minus in the quadratic formula says, if this one or this one, they both work, right? That's not true here. We're not saying that they both work, okay? You have to make a choice. Okay? It's a little deceptive. We don't really mean plus or minus. We don't really mean both values. Okay? So doing this one, let's look at part A on those examples, and then we'll stop for today and can pick this up on Monday. Part A says we want to use sine of 15. We did sine of 15 before with a sum and difference formula. We're going to do this one with a half angle formula. What is 15 degrees half of? 30. Good. So using our half angle formula that we just developed, this is plus or minus square root of 1 minus cosine of 30 degrees all over 2. Remember again, what's under the square root, that cosine that's under the square root, the inside of that is double what the inside is for the function that you're looking at. Okay? Do I want to use the positive or do I want to use the negative in this case? What do I look at? To determine if I'm using the plus or the minus, what do I look at? The quadrant the 15 is in, right? I want to look at this one. 15 is in quadrant 1, so we'll use positive. Good, fantastic, exactly right. So we're going to cross out the minus sign. And again, that's because 15 degrees is in quadrant 1. So I'll just square root of 1 minus cosine of 30 is root 3 over 2. Any questions on that one? Okay. We'll do the other examples next time, as well as develop our half angle formula for tangent. And we'll do some examples next time. Probably get into some of your product of sum formulas as well. Anyway, have a good weekend, everybody. See you on Monday.